Hi. So good morning, everyone. Today we have as our speaker Gabriela Lichtenstein. And Gabriela did her PhD at the University of São Paulo and spent some period at Fermilab as well. Then she went to the University of Campinas and then New South Wales University in Australia, also as a postdoc. And now she's here at IIP. And she works with particle physics phenomenology in colliders. So today she will talk about the Triality model and charge Lepton flavor violation. So take it away.
Okay, thank you very much. Thank you for inviting me. I'm happy to be here. I know I was already introduced. It's just that I didn't do only collider physics, and I have an uneven path until here. So I just wanted to tell you that I did my master's and PhD at USP, and it was mostly LHC phenomenology on beyond standard model. However, when I got to Fermilab, they were doing everything else. So I had to study dark matter and cosmological bounds and everything that was going on at the scene at the time. So it was a big change. Then I had a very long period for the pandemic break because my position at Australia, they closed the borders and I couldn't go for 2 years. So 6 months of those 2 years, I got a postdoc at Unicamp, and it was in a third area. It was experimental particle physics with the neutrino group, and we did analysis for measurements at kaon and argon. Finally, got to go back to UNSW in doing collider phenomenology, and now I'm a postdoc at IIP. So my main area is collider phenomenology, but I do have some experience in other areas in particle physics. So we start from the beginning with the standard model. The standard model has those 3 families of fermions divided by quarks and leptons. The main difference between the quarks and leptons is that quarks are charged under color, so they can interact through the strong force. Then we have the gauge bosons, the gluon for the strong sector, photon electromagnetic, and the weak bosons Z and W. And the Higgs boson as well. That was the last part that was found in 2012. So the symmetry that describes the standard model is the SU3 color times the electroweak sector SU2 cross U1. And we have to introduce the Higgs mechanism to break the electroweak symmetry into the U1 electromagnetic. This way we can describe the 2 bosons that are massive, otherwise they shouldn't have masses as the gluon and photon, and they do have 90 and 80 GeVs. So the standard model is extremely successful. It has very precise measurements. This is just one example. This is the measurement of the mass of the Higgs and the mass of the top that you can find on PGG. So the direct measurements of the Higgs is in yellow, and the direct mass of the top is the 2 vertical lines. Okay. Then you have indirect measurements that are taken with precision with higher order calculations. For instance, the width of the Z boson, the Z polar symmetry, and the mass of the W. And they all converge to this red region. So this is very precise, and they're all in accord. So if it's all working so well, what are we looking for? Well, usually I put about 3 questions to illustrate. Now that we have all those AIs, I asked them the list of the main questions, and they'd answer me about 20. So maybe the students, they can tell you what are their favorite one. Someone? Uh, so these are the beyond standard model questions. Our group works mainly with dark matter. So the standard model doesn't include dark matter. I think they are a bit shy, so I can say something. So we have a lot of questions, including dark matter, dark energy, including gravity at the standard model, the neutrino masses, so the neutrino can oscillate, and that indicates that they have masses. I'm not going to read all the 20 questions, so it's just to illustrate how far this can go. And well, we are physicists, so we also always can make one more question, right? And I also ask the AI to give me the main ongoing searches. So it's not only the LHC. We have a lot of experiments. They are also not all of them in here. The Lariat collaboration that I'm part of is not in here, for instance. But we have the high energy colliders, the LHC and Bell, that are ongoing. And we have many more experiments on flavor physics, fixed target, neutrinos, cosmic rays, and dark matter. But today I'm going to talk about collider physics. So I wanted to emphasize two things before I start showing you how things are, showing you the experiment itself. So if you want to look for new physics, and you want to look for a heavier particle that is new, for instance, you can always think about an experiment that increases the energy, and then this center of mass energy that is very high can produce your particle. However, there is another effect, which is the luminosity. So the luminosity is the measurement of potential collisions measured in inverse femtobarns. Thank you. Measured in inverse femtobarns. So we can always increase the luminosity, so we increase the statistics and we have more precise measurements. This is very important because we want to see quantum effects on these precision measurements. So if you've taken already a QFT course, you would have seen some pictures like this, where you have the interaction, and this is actually a sum in your expansion. This comes from a Dyson series. And if you take the first order, you have what you call the tree level. However, we do have contributions at next to leading order with those quantum effects, those loops inside our interaction that will give you a correction. So if you have a model with new physics and you're looking for a heavier particle, they will contribute at loop level in, for instance, electroweak measurements that we already know. So if we increase the precision of the electroweak measurements, we can also look for heavier particles in new physics. Okay, so I need to talk a little about the LHC, the Large Hadron Collider. This is a proton-proton collider in Switzerland. It's the biggest we have in the world, with the highest energy we ever reached. Just a note that Brazil is now officially an associate member since last year. And the timeline of the LHC is pretty large. So it started in 2011 at 7 TeV energy. In 2012, we had the Higgs discovery, just 1 year after. And then you have the run 1, 2, and nowadays we're at run 3 with an energy of the center of mass at almost 14 TeV, 13.6. The next step will be the high luminosity LHC, should start around 2029. And as the names say, high luminosity, we are increasing the luminosity. So if you notice here, we also have the luminosity of the LHC starting at 30 inverse femtobarns. Today it's at 450, and the high luminosity should reach 3 inverse atomers. It's 1,000 difference here. So 3,000, sorry. The integrated luminosity, so it's the luminosity over the whole program, which should reach 3,000 inverse femtobars. There is another experiment ongoing on Keiki, Japan, which is BEL2. This is an electron-positron collider. The energy is lower. The center of mass energy is 10 GeVs. This is because they focus on flavor physics, so they want to produce B quarks at 7 GeVs. However, they have the world record instantaneous luminosity, and the projected integrated luminosity is at 50 inverse atomers. So this is really high luminosity. And there are many proposals for future colliders. So nowadays in our conferences, there is always the discussion of the proposals of the future colliders and their sensitivities. So the proposal from CERN is the future circular collider. That would be a ring even bigger than the LHC. They would have many different phases, including electron-positron at the weak scale, and then a Higgs run at very high energy, about 100 TeVs. There's another proposal, ILC in Japan, which is electron-positron linear collider, also for precise measurements. So it is high luminosity at a lower energy. And proposals from muon colliders, which are very high energy. So let's go back to our beyond standard model questions. Today I'm going to talk to you about flavor physics. So flavor physics wants to explain mainly the structure of the fermions. Okay, so why there are 3 families of quarks and leptons, explain their mixing, how they are interacting with each other. The fermion mass hierarchy, for instance, you have the electron that is extremely light at half MeVs. Then the muon is 100 MeVs, and the tau is 1,000. So why do we have this hierarchy of the masses? The neutrino masses, we know that they should exist from neutrino oscillations. And today's topic is charge lepton flavor violation, which is a bit inside of the mixing patterns question. So we want to explain the interactions between those 3 charged leptons, electron, muons, and taus. Let's first take a look at the muon decays, okay? So there are leptonic and there are hadronic decays. I'm not going to touch the hadronic decays today, just the leptonic one. So the decays, they decay into leptons. The main channel is this one. It's mu, 2 electron and 2 neutrinos. 1 neutrino from the electron and 1 from the muon. Anti-neutrino from the electron, sorry. So if you look at the diagram, you have a vertex with a muon and a neutrino of the muon, and the second vertex with the electron and an anti-neutrino of the electron. So there is a conservation here with the leptonic family. We see that muon only interacts with particles from its own family. There is, however, if you include lepton flavor violation, you can generate a decay with the vertices that is a muon going to electron. So we break the individual lepton number, which is not the lepton number, there are 2. Okay. So these vertices that are mu to electron would allow processes such as mu to 3 electrons or mu to E gamma. And we have many experiments trying to measure that. The bounds we have today is from MEG2 syndrome, and mu through E. So the standard model, it does describe the similar mixing through the quarks. So the quarks are allowed to change the families within 1 vertices. And this is because the interaction eigenstates of the quarks are not the same as the massive eigenstate. So when we describe the mass terms through the Higgs Yukawa interaction, we obtain a non-diagonal matrix, and we need to rotate those eigenstates to obtain the mass of the quarks. And this is done with, this mixing is described by this mass matrix called CKM, Kabibu Kobayashi Maskawa, sorry. So this is very well done in the standard model. But the standard model does not predict those kind of interactions through the leptonic sector. And we have one more observation, that is the neutrino oscillation. This is already beyond standard model. We see that, for instance, if the neutrinos coming from the sun that are produced in the sun, they're expected to arrive at Earth with a certain proportion between the neutrinos of the electron, mu, and tau, and the observed pattern is different. So this is an indication that the neutrinos can oscillate. In the path from the sun to here, they can change the flavor. And so this is an indication we can break the individual lepton numbers for the neutrinos. So if the neutrinos can do it, the quarks can do it, why not charged leptons? And we have many theories beyond standard model that does predict the charged lepton flavor violation. However, as I showed you with the muon, they have very strict experimental bounds. We have never observed that. Especially in muon decays and electron-muon conversion. This is from muon to nuclei scattering. But the charged lepton flavor violation with the tau are much less constraining. This is because we cannot detect a tau that easily as an electron and a muon. The tau lifetime is only 10 to the minus 13 seconds. That's very short. So unless you're in very high energies, you would not see the tau, but only the product. Sometimes with very high energy for it. In the TeV level, you can see a few centimeters of the tau. So we introduce here this model of lepton triality. And the interesting part is that it allows the charged lepton flavor violation, preferably in the third family. So we avoid the experimental bounds between mu and electron, and we can look for rare tau decays. So this model, it aims to explain this lepton mixing pattern. It does not explain the masses of the leptons. And it's motivated by flavor structure models with an A4 discrete symmetry. So this symmetry will be broken into two sectors, a Z3 charged lepton sector and a Z2 neutrino sector. So that is that parity symmetry. And just a note here to understand the following steps. The A4 is generated by combinations of two matrices S and T. They have this cyclic relation. So for instance, T to cube is always 1. So we can describe it with those matrices that is diagonal with an exponential of 2 pi I. And here we have just one number changing between the three elements, which is 1, 2, and 3. So this 1, 2, and 3 will become our triality charges. Okay. So the break of the A4 generates the lepton sector with the Z3 symmetry that inherits this T matrix, such a way that we're going to rotate the leptons. So if you remember the quarks, we need to rotate them to reach the mixing pattern to the CKM. This is a similar mechanism. We need to transform the leptons, such as omega, which is the 2 pi I, power to the T, that is a charge, that is the triality charge, times the lepton. We need to write the Higgs and quarks as singlets under triality, and the Yukawa sector that's going to generate, for instance, their masses, needs to be diagonal under Z3. So when we do that and we expand, we can identify the triality charges 1, 2, and 3, and charge the electron muon and tau T equals 1, 2, and 3. Okay? And the interesting part is that the triality charge, it must sum modulo 3. So it would not allow the muon decays that we have extensively looked for in experiments, but only the tau decays that have less stringent bonds. So for instance, if muon going to 3 electrons, the initial triality charge of the muon is 2, and the final, the electron is 1, so the final would be minus 1 plus 1 plus 1, that is 1, and the delta T is 1. So this is not summing 3, and it's not allowing. However, the tau charge is 3, mu plus is minus 2, and the 2 electron is plus 1, so this sums 0, and the difference between them is 3, so this one is allowed. The model we build can generate actually 3 different theories, because it will be mediated by those doubly charged scalars k. And k can be charged at the triality 1, 2, or 3. So if t equals 1, we have those 2 interactions where the doubly charged scalar k1 would have the coupling f1 and 2 with that can interact with tau mu or f2 EE. So we generate those 2 vertices. The t equals 2 is k2 with g1, 2, tau E mu mu, and t equals 3, we have h1 and h2 with mu E tau tau. So these originated the first work my collaborators did just a little before I arrived in Australia with Ines Bigaram. And they did a phenomenology at Bell 2 looking for rare tau decays. So we can calculate the branching ratio of those decays and compare it with the present constraints from Bell and the projected sensitivity for Bell 2 at 50 attobarns. This results in this parameter space where we calculate the branching ratio depending on the coupling F1 and 2 for t equals 1. There is a similar one for 2 and 3. And the mass of the scalar at 1 TeV and 5 TeVs. So we see here the present bounds on these full lines here, and the dashed lines is the projected sensitivity for Bell 2. The work we did was to study the phenomenology at Lichtenstein. So Lichtenstein is a proposal for a next collider at J Park in Japan. So J Park already has 2 experiments. One is G-2, the other one is Tristan. So G-2 is a muon experiment with ultra-cold muon technology. So they would use this technology to make a collider with the electrons coming from the Tristan experiment. That's why it's mu-Tristan. And there are 2 different proposals. One is to make a mu plus collider at 2 TeV, the central mass energy. So 1 TeV for each beam. And the expected luminosity at 12 inverse phantom bars. The second proposal at mu E, we would have an asymmetric beam energy. So the mu plus can go from 1 to 3 TeVs, and the E minus at Tristan is only 30 to 50 GeVs. However, the luminosity is very high at 100 inverse femtobarns per year. So we listed here all the processes the triality can allow for 2 lepton scattering at 3 level. So t equals 1, we had those processes, then 2 and 3. And we can see here that mu Tristan is able to probe 5 different channels, and 3 of them have charged lepton flavor violation. So this is the result, one of the results for the mu plus collider. So we're analyzing here this channel of mu plus at the t equals 2 model, producing tau e. So this has 2 effects. It has charge lepton flavor violation, and it has another effect that is the resonance searches at colliders. So when we produce a new scalar, we can also look for the resonance at its mass. So if you see here, our plots has a little resonance. That is a different search for the experimental part. This is our parameter space with the couplings G1 and G2 and the mass of the scalar. So we calculate the cross section and we do the contours at 90% limit, assuming no background. That means the number of the events, that is the cross section times luminosity, is at 2.44. So these bounds were obtained like this. And we have here also the limits from the LHC direct searches for doubly charged scalars. And in gray area is the Bell present constraints. The dashed line is the Bell 2 future sensitivities they have obtained in the past study. And blue, green, and brown is the 90% counter, assuming a center of mass energy at 1, 2, 3, and 4 GeVs. So this is quite interesting because they are near the Bell 2 region. However, this is the whole Bell 2 projected luminosity, and our curves is only 1 year of mu Tristan. So if it runs for 5 or 10 years, it would probably surpass Bell 2. Yes, usually at the maximum, but this is a parameter space with the number of events, and the searches we do with the maximum would be an histogram with the number of events that is a bit different from that. So it's a different plot. But it does have an effect from the resonance. The other kind of analysis we did was for the mu plus E minus collider. So this is a bit different. The E minus would have a lower energy, so the center mass energy is much lower at 0.346 and 775 TeVs. Also, there is a big restriction here because the muon, it decays easily, and a muon beam would have a lot of radiation. So there, in the proposal, they also have a shield around the muon beam. And this is also restraining our calculations in the curves here. But we still can do the phenomenology at the t equals 1 and 2 models with electron muon going to at t equals 1 tau e and t equals 2 mu tau. So this is one of the results at t equals 1 with the couplings and the mass of the doubly charged scalar. Again, the pink area is the LHC bounds, Bell and Bell 2. And here we have the projected sensitivity for mu Tristan with those 2 center of mass energy. So they are lower than Bell 2, but again, this is 1 year of Lichtenstein and the whole Bell2 projected sensitivity. So it could be different in many years of Lichtenstein runs. So we resumed all the phenomenology of the table with the Bell, Bell2, and Delphi constraints at 90% limit. So we have all the constraints to the couplings and the mass here. And these are the Lichtenstein channels we analyzed. So what is important here is that our results are comparable to Bell2, so we think they are complementary. And this luminosity again is for 1 year, so it could be even more precise. Also, this scattering would have different measurements of only G2 that is not measured in the past experiments. Do we still have time? Yeah, okay. Now this is another study we made in the same topic, which is the next leading order constraint. So now we're taking the one loop. I forgot the word, sorry. We're taking the one loop. Okay, so it's the next leading order interactions. So this is the potential between this is a general doubly charged scalar potential that we had in the triality also, but you can reach it through other models. So for instance, we have neutrino masses models that also have doubly charged scalars. So it is interesting to look for them. So the potential here, we have the interaction between the doubly charged scalar and this phi field, which will generate the Higgs boson. Okay, so we have an interaction, fourth interaction, kappa phi, between the two phi's and the doubly charged scalar. Also, the Yukawa interaction with the leptons, it is similar to the triality charges, so you can reach specifically this scenario with F1, G1 and 2, G1 and 2, and H1 and 2, with this Yij, which is the Yukawas in this scenario. So we have 3 channels that we can look for, 3 different interactions. We can generate loop effects, that's the loop effects at Z to 2 leptons, Higgs to gamma gamma, and Higgs to Z gamma. So just explain a little how those calculations were made. We have a diagram like this one, so Z to 2 leptons, and we can calculate these vertices, gamma L mu, like this. This is the result. If we go one loop, we can calculate each one loop interaction, which are a lot of loops of interactions, and estimate and calculate the analytic formula for a delta GR. So we make this renormalization with the GR plus a delta, and we have an analytic expression for delta GR. On the other hand, each experiment has its own precision for those measurements. This is LEP. LEP is the last accelerator before the LHC. LEP and SLD, that's another experiment. Measurements for delta GR, E, mu, and tau. So these are present constraints. And we can also find in the literature the expected precision for ILC plus the high luminosity LHC. ILC at GigaZ, that's quite interesting. ILC is planning to have one run dedicated to the Z pole. So it's going to produce a lot of Z bosons and increase the electroweak sensitivity. So this is the run at a specific Z mass with the center of mass energy. Then we have CEPC, which is another proposal for Lepton collider, and FCC-EE plus the high luminosity LHC. So we are comparing directly our analytic expression for this model with the precision of each experiment. Okay. Now these vertices here, we have one loop diagrams from the standard model. It's a lot of them. I could not draw all of them here. Plus those two loops contributing with the doubly charged scalar. So calculating all of these, comparing to the limits of each experiment, we have those parameter space with those curves. So here we have the coupling with the UCAL interaction Y, dagger Y. This can be traced back to the triality model. And the mass of the doubly charged scalar compared to LEP, ILC at GigaZ, CEPC, and FCCE. Again, this area here is the direct bounce from the mass of the doubly charged scalar at Atlas. Okay. Then we have a similar calculation for Higgs to gamma gamma. The contribution of new physics would generate those two one-loop diagrams, and we can calculate the width, that is the decay of Higgs to gamma gamma, and calculate the ratio between the new physics plus standard model interaction divided by the standard model expected value. We compare this to the Atlas results of this observable, which is 1.088, and reach this plot, which is kappa phi. Kappa phi is this interaction between Higgs and the doubly charged scalar, and the mass of the doubly charged scalar. We have this allowed region for the LHC, and the bounds again for the direct searches of the doubly charged scalar. Now this is the projected sensitivity for future colliders at Higgs to gamma gamma. So they do not give us the results in terms of the ratio R gamma gamma, but in terms of kappa gamma. It's not the same kappa, I'm sorry about that. This is kappa phi, this one is kappa gamma. And it's just a square root difference. So the high luminosity LHC should have 1.8% at delta kappa gamma. And we can also have future E plus E minus colliders. They all have around 1.3%. And the integrated FCC program, that is EE, EH, and HH, that would have a very precise measurement of 0.29. So here we have the parameter space of the coupling and mass for high luminosity, E plus, E minus, and FCC integrated program. Now the last part, we have the results for Z gamma, which is similar to those results we did for gamma gamma with RZ, with delta Z gamma. However, most of the experiments we were looking for, they have a very high delta kappa gamma, delta kappa Z gamma, about 10%. This would not restrict our parameter space. So the blue one here is about 3%. The only restriction we start to have in brown is the full FCC program, which is possible, but it will take a lot of time to reach. We should have the high luminosity run, build the FCC, build 3 programs of FCC, then have the full program. This should take a lot of time. But it is possible to test this Higgs to Z gamma channel. However, we did do a ratio between the Z gamma and the gamma gamma ratios, and it is pretty small, about 0.3. So the gamma gamma channel is much more likely to have a signal than the Z gamma. So these are all the channels we have studied. in summary, I have presented to you today the Lepton Flavour Triality, which explains the mixing pattern of the leptons, and has this very interesting property that would allow the bounce from muon decays and would not allow the muon decays that have a strict bounds, but allow preferably interaction with the third family with rare tau decays. So these generated this first paper with predictions for BEL2, and then we compared them to the proposal for mu-Tristan future collider and mu plus and mu plus E minus collider. And we have seen that it could generate 3 different charge lepton flavor violation channels and resonance searches for the doubly charged scalars. So we see that Bell and mu-Tristan are complementary. In 1 year of mu-Tristan, we can reach the sensitivity, we can reach something similar to the sensitivity of the full Bell2 program. And then I also showed the results at next leading order for Z2 lepton, Higgs gamma gamma, and Z gamma, and their projections for the precision at future colliders. Thank you.
Thanks, Gabriela. Let's open for questions.
Thank you, Gabriela. I think I missed this in your talk. So triality models, what are they good for?
Let me go back. So in the literature, we have flavor structure models where they test different symmetries that would explain how the leptons would mix to each other.
So mixing in this case will be like, what exactly they explain about the mixing? Ratio of masses or?
No, it's the interaction.
Angles?
It's the interaction. Sometimes they also explain the masses, but it's pretty much the interaction. So the quark sector, we have the interaction eigenstates that are different from the mass eigenstates. So we need to rotate those. If you just do a Yukawa, it would be an off-diagonal matrix. We have values all over. And we want it to be diagonal for the masses to be only the mass of the up, down, and charge. Up, down, and top. No, up, charm, and top, the 3 generations, sorry. So we need to rotate those eigenstates to obtain the masses, and we have 2 different eigenstates, the mass eigenstate and the interaction eigenstate. So the masses are diagonal, and the interaction, we can have vertices of quarks changing their generations. But we cannot do that for leptons, because the lepton matrix is already diagonal, so we don't have any predictions. Okay? Can you understand a little?
Yeah, but what does triality does here? Like
So
how does it solve it?
the problem, the big problem, is the neutrino. Because the neutrino oscillation, we do allow those vertices to appear. And the neutrino is massless. So when we do that for the quark, we reach the mass quarks, the quarks of the mass of the quark. If the neutrino can oscillate and we make a new CKM that is called PMNS, then the neutrino would be massive also. So we don't know if the neutrino are massive or how they do this flavor oscillation. And we would have to introduce neutrino masses for this. So there are 2 areas, they are similar, but there are 2 different areas. You have the neutrino masses theories, and we have flavor, forgot the name I just said. sorry, and we have this flavor interaction patterns. Okay, so we need to explain both of them. So in literature, when they want to explain this flavor structure, why, if there is a symmetry behind all of that, it's called flavor structure. So it could have an A4 that generates all of that pattern from quarks, leptons, and neutrinos. We have models that are looking like this. And there are many different models with different symmetries. So this one is very popular. We have many studies with A4 discrete symmetry to explain this pattern between quarks, leptons, and neutrinos. And the flavor that triality, it is motivated by the models that break A4 into those two Z3 and Z2 sectors. So the first time it appeared, it was to explain something called neutrino 3B maximum mixing. I don't think it works anymore. The neutrinos now, we would have to break the triality and add some neutrino models to the triality charge. But the leptons, we still can study them. So we would have a Z3 charge that inherits the structure from the A4. And these would explain the charged lepton flavor violation patterns we see.
Thank
Is that
you.
okay?
Yep.
Thank you, Gabi. My question is, where your new physics appears in your model, just in the scalar sector? I mean, we have...
Charged lepton flavor violation.
Okay, but I mean, in terms of new particles interactions, you have only these K particles in the scalar sector?
Yeah, to have a heavy resonance, which is a doubly charged scalar. And we want to generate the charged lepton flavor violation, so we have different interactions between the leptons. That's why you have a big list of scatterings. So a lepton collider, we have many proposals of lepton collider in the future. We made this big list of which ones could be probed in the triality sector.
Yeah, but in this case, these processes, they are allowed by, I mean, the interaction is through the gauge boson that we already know, right?
No, they can be through the doubly charged also. So if you take the first, this one, mu to tau e.
But I mean, what is the mediating particle?
Yeah, it's the K, doubly charged
so
K2.
this is the new physics in terms of it's a scalar. So the new physics in terms of new particles would come from the scalar sector, just.
Yep.
So in this case, these particles, they are, okay, this is doubly charged.
And it has to be heavier than
Yes.
something near 1 TeVs, because otherwise we would reach this pink region that is the direct searches of the LHC for doubly charged scalar.
Okay, thank you.
Okay?
Any more questions?
So these K scalars are not Higgs scalars.
No, the
They're
Higgs
charged.
is singly charged.
Yeah,
This one should be doubly charged, has 2 charges.
yeah.
And they interact with each other. So this is the potential, and they can interact with each other. For instance, at this term, kappa phi, you have phi that will generate the Higgs.
So
and
phi are the Higgs.
this is before electro-Higgs symmetry, so it's not quite the Higgs boson yet. but it will generate the Higgs boson after symmetry breaking. And K would be our new doubly charged scalar. It's two different fields, yeah.
And the idea is to use these scalars, charge scalars, to explain the non-mixing?
The new mixing, yes. It has applications in different models. So we have, for instance, neutrino mass models that also have doubly charged scalars. So this second paper we made the potential, which is the triality potential, but we made them a general doubly charged scalar potential that could be also applied in different scenarios. Yes.
Okay. Suppose I wanted to test supersymmetry. What I would do? What your guess would be? What kind of
supersymmetry is a completely different theory. It can generate the mass. I think the mass hierarchy. No, I might be saying something off. So it's been a while I don't study supersymmetry. Sorry. So supersymmetry would generate a spectrum that is similar to the standard model, but the fermions would become bosons, and bosons would become fermions. And this was very motivated at the LHC, it still is. So we have the hierarchy problem, we have the Higgs boson, which is a scalar field, right? And when we calculate the Higgs boson with the top loop like this diverges at the logarithm scale. So our plot is something divergent, and we needed to have a new physics to include here and have a resonance, right? So if you include supersymmetry, then you have a scalar with a stop, and those two diagrams, they cancel each other exactly. So this was a big motivation for the LHC to look for supersymmetry. However, we have run since 2011, and we have not found the stop. I think the stop limits today are over TeV scale. So this model, that is the minimal supersymmetric model with supersymmetry, is very restrained. People still look for supersymmetry, and there are still models, but they are a little different from this one, this scenario. So my PhD, we did something called folded supersymmetry. This is quite interesting because we would have the color group and a dark sector color group. So the stop does not interact with the standard model. This one would have a dark color, and this one would have a color. So we have folded supersymmetry, twin Higgs, a lot of models that would have these. And then we can solve this, that is the Higgs hierarchy problem or naturalness. We have a natural problem, but our spectrum would be in a dark sector, would completely different. So
much higher energy?
No, it's not higher. It doesn't interact with the standard model because it's a different color group.
Okay.
So it could be produced at the LHC, but if it was produced two stops, so if it's two stops and they are charged under color, they would decay into all different hadrons. And you see a jet. But they are not, so they will form a globule that is also dark. It's not going to interact with the standard model. So the signal we would have in this case is that the globule would run a little, you'd see nothing, and then it would decay with a Higgs portal to something else. So it's a displaced vertices. It's a very different search.
Okay, thank you.
More questions? Okay, if not, let's thank Gabriela again.
Thank you.